Now we're going to look at another common mathematical function, that is e raised to the power of x. So we're going to generate the Taylor approximation to this function. Now e raised to the power of x mathematically is sometimes written as exp and then the x value. So the Taylor series approximation for this is 1 plus x squared upon 2 factorial, x to the 3 upon 3 factorial, and so on and so forth. Now we're going to generate the approximation using these 5 terms here. So the number e is simply just a number. It's approximately equal to 2.718. So the e to the power x is really 2.718 raised to the power of x, where x is the real number line here. So for example, if x was 0, we would have e raised to the power of 0. Anything raised to the power of 0 is just a value of 1. And you can see it heads off to 0 as we go along the negative axis, x-axis, and it heads off to infinity as we go along the positive x-axis. So let's have a look and we will see what our approximation looks like. Now you can see here that approximation is in blue, and it's a good approximation from a value of around -1. So, but whenever the number gets smaller than -1, our approximation goes off. So we could therefore say that the bounds of our approximation may well be from, say, -1, and then we would have to pick a positive bound. Now I'm not doing this particularly scientifically, we're just doing it a bit of hand in eye, okay? So we could head off really up to possibly maybe a value of 2, okay? So we could say that we can generate the Taylor series approximation to our exponential function from the limits -1 to +2. Now if we wanted to generate it with a greater approximation, we could add more and more of these values. But this will do for us for the moment. We just have to make note whenever we generate the literature for the CPU, when we use this fixed point method, it's only accurate and it can only be done from the values -1 to +2. And in fact, what we could do if we wanted to is to add a little trap. So it will test the value and see whether it's less than -1 or if it's greater than 2. And if it is, then it'll come up with a trap and it will say we will not generate this number because it's out with the not the range, it's out with the domain of the input value x. So now we've seen what the function looks like, let's go ahead and we will see it in the assembly language. So the right hand side is the calling function, the left hand side is the routine. So the calling function is just simply the same as the previous ones that we've seen. We're going to push the value x onto the stack and then we're going to pop it off within the subroutine. And then it will run through the subroutine and then it will push the answer onto the stack and then we pop the answer back off the stack into exp. Now we're going to work it out for a value of 0.5. So the x is 0.5 and we're working out 2.718 raised to the power of x. Now this should give us a value of approximately 1.649, which in our fixed point system is 0 cross and it's going to be 01A6. Okay, so we're looking for 01A6 for the final answer. So that's the calling function. The actual subroutine are written up here, and again I'm not going to go through it in a lot of detail because it's just the same as previous ones. So I've written the Taylor series expansion here for the first 5 terms for the exponential function, and we've worked out the actual polynomial values here, and you can see the values here, and then I've generated them here within the subroutine. So these are just calls to the floating point power function, so which just generates these polynomial values. So that's the code. Whenever it's finished, it pushes the value onto the stack, and then we pop it off over here into the memory location exp_x. So let's see this actually running within our machine. So I have loaded the subroutine into the ROM and the program into the RAM, and it's running here. So when it finishes, hopefully if everything is right, we should get the results here. So it should be 0 cross 01 A6, and that's equivalent to 1.6487. So I will allow this to run, and then when we get the answer, I will start the video again. Now that's the simulation finished. Let's go in and look at the final result. We were expecting the result 01A6, but we have the result 01A5, so we're only 1 unit out. Now let's go ahead and we will see the percentage error for this approximation. So I have ran up the little conversion tool. The answer we get is 01A5, and that's this value here, 1.6445. So let's add this to our diagram and we'll see how close our approximation is. So I have added our values into the graph here, and you can see that we have actually a very good approximation. So the line in brown is the actual e to the power of x, which should be 1.6487 at a value of 0.5. Now the Taylor approximation is this value here, which is 1.6484. So you're only talking about that's 3 10,000ths all out. Okay, so the actual Taylor approximation and the function are actually very, very close. Now the value that we generate is a value down here, which is 6445. So from this point up to this point here, the percentage error is only 0.03%. So you can see here that we've actually got a very, very good and strong approximation. And you can see when I zoom out, it gives us an indication of the level of approximation. So that's all for the exponential function. In the next video, I will just go through a quick list of common Taylor series functions, expansions to common functions. Now we're not going to go ahead and generate all of these, but it's easy enough to generate them, and you've seen me doing it over the last few videos, and it wouldn't be difficult for you to go ahead and just do that for yourself if you want to generate particular functions that are of interest to you. So thank you for listening. I'll get you on the next video. Goodbye.